how old he is sometimes. I get a little shocked. How old he is when he says
Oh, I love these. They're like the binder notebook things, right?
oh yeah. I take the notebook inside, came in the front, and math in the back.
All right, morning everybody. Time to get rolling here. So this is Dr. Lyle, who does demonstrations for us and outreach in the department. If you're interested in any chemistry outreach activities in the schools and things, he's the guy to talk to. So this week we're going to get rolling on Unit 1. Remember, there are unit plans that are posted on Sakai that sort of have the plan for each unit, including readings, and textbook problems, and all that sort of stuff. So today is an intro overview. Sapling is due Tuesday night at 11:55. I'm sure you'll all be just waiting until 11:54 to quick submit your answers. But so I'd say 85 to 90% of you are signed up for Sapling. Excellent. And a bunch of people have actually completed it or are on their way, so that's a good thing. Wednesday, we're going to do the first individual and team readiness assurance test, so it'll be like we did the other day. There'll be a Scantron part that you do on your own, then you do the scratch-off thing as a team, and then we'll talk a little bit about questions that maybe were troubling to you. And then Friday, we're going to start doing the first application. So these are going to be worksheets that you'll work through. Remember, we did an example with the diagnostic quiz where there was an ideal gas problem. It's going to be that sort of thing, but there'll be a series of them having to do with the Unit 1 material. Okay? And then this week, remember that you're supposed to go for your 1-hour intro lab meeting, either I think at 1:25 if you're an odd group, or 2 something or other if you're in an even group. Okay? All right, so let's talk about Unit 1. So this is thermochemistry. I like to start with this because energy, as you'll see as we go through the semester, underlies our understanding of a whole lot of different topics: atomic and molecular structure, equilibrium, kinetics, all these sorts of things. And so that's a good way to get oriented. Plus, it will hopefully jog your memory about a few things like stoichiometry and balancing reactions and all that good stuff that we are assuming you did at least once in the dim past. So first thing I want to talk about is types of energy. As you'll see from the point of view of thermochemistry, you kind of look at a big picture version of this, but underlying that, there's energy associated with a large group of molecules, but there's energy associated with each of the individual molecules, and we're going to talk about that as the semester goes along. And you learn in elementary physics that there's sort of 2 classifications of energy. There's kinetic energy, which is energy of motion. So if I have a particle of mass m and it's flying along with some speed v, then the kinetic energy is 1/2 mv squared. Okay, so that's the energy associated with the motion of something. We also have energy of position, which might be gravitational. So the gravitational potential energy is bigger here than it is down here. And so there's potential energy, which is energy of position. And as an example, we have in atoms charges that are attracted or repelled from each other. Protons, electrons, electrons, electrons. And so if I have 2 charges with charges Q1 and Q2 that are a distance apart r, then, for example, the potential energy for that Coulomb charge potential, electrical energy, we might write as V, which is often used for potential energy. That's a function of how far things are apart. And this would go like a constant times Q1 times Q2 over R, okay? And we're going to come back, we'll see that. We're not going to deal with it in detail, but that underlies the structure of atoms and molecules. So this is sort of the most basic classification of energy from the point of view of physics, but in chemistry we're often looking at things on a somewhat grander scale. And so we sometimes divide energy up into other pieces. So we can talk about the so-called thermal energy of something, which is related to the temperature. And the temperature of an object has to do with the average of all the kinetic energies of the molecules flying around in there. So this is related to the average kinetic energy, and it has to do with random motions of things. So it's a randomized kind of energy. We have gravitational energy, for example. We're not going to worry about that so much this semester, but it's obviously important in physics and things. We have mechanical energy, which can come in a bunch of different forms. We're going to be interested to some extent in what we call pressure volume energy, and we'll talk a bit about that today. There's electrical energy. We won't do a lot with electrical energy this semester, but if you hang around long enough to take Chem101DL, we talk about batteries and electrochemistry there, and electrical energy is obviously very important there. We have electromagnetic energy related to electromagnetic fields, and we are going to talk about that from the perspective of light, because one of the ways we learn about atoms and molecules and do things to them is have them interact with light. So we're going to look at that. And then finally, we have what we sort of call overall chemical energy, which we'll look at a lot. Chemical energy has to do with energy that's stored in bonds of molecules, or in stretching bonds, or in interactions between molecules. And so to illustrate some of this, the fabulous Dr. Lyle, who's here today, sorry, I have to do that every semester, is going to show you his fancy-dancy car. You got the old one and the new one. Wow.
Definitely. So anyways, I was asked to show you about the first law of thermodynamics, which means energy is conserved. It can be transferred from one kind to another kind to another kind, but the total amount of energy is conserved. That means it's not created, it's not destroyed, it's conserved. And in this first model that I have, which is my old model, until I broke the, whatever you call it, fuel cell. And so we're going to look at solar, or abbreviation EMR, electromagnetic radiation, and we're going to change it into electrical. And we're going to use a solar cell to do that. And then we're going to change that into mechanical. Using direct. So here we have this car. It's kind of useless. It's not going anywhere. But if the sun is out, and our motor is connected, we have a disconnection, so your car doesn't work. Okay, so we have the sun out. Sun is hitting the solar cell, which is converting the light energy to the solar panel into electrical energy, where then the electrical energy is being used to drive the motor, and the wheels turn. So all you really need to drive your car is the sunlight and the solar panel that creates enough electricity to operate the motor in your car. The problem with this is, what about if there's no sun? You can't go to the movies, you can't go to the mall, you can't go anywhere. So this is not a good answer. It's only good when the sun is out. There we go. So it's kind of useless. Okay, so we've developed these fuel cells, which when you go take 210, you'll get more of the idea of how it works. But again, sunlight is used to create electrical energy. So we have this part, the EMR, going to the fuel cell, well, going to the solar panel to create electrical energy. And that's what the solar panel is for. And then that goes to the fuel cell, which is going to take water, which does not naturally turn into hydrogen and oxygen, fortunately. That mixture is explosive. But it will take water and rip it apart into hydrogen and oxygen. And so we're going to take water, convert it into hydrogen and oxygen, and so we will have stored energy in the fuel cell, or in the hydrogen and oxygen created by the fuel cell, which later on can be converted back into electrical energy, which then can be used to drive our motor, mechanical energy, to go someplace. And these two tanks right here, which way back there you can't see very well, they're slowly converting the water into hydrogen gas and electrical gas. I should have brought my balloon to show you there's a lot of energy in hydrogen and oxygen. And so we can use that stored energy that's in those two substances, and we can extract the energy out. With a balloon filled, we would ignite it and it would go kaboom, send a shock wave through the room, and your ears would vibrate, so I don't want to do that for you. But this process is pretty slow, and we don't want to take 10 minutes or so. So another way that we can do this is we can take batteries which already have energy stored in them. This is a short instruction. We can put our battery in here, connect it up, and turn on the battery, and this will do the whole process a lot faster for us. So we have these two tanks. These two tanks are collecting the hydrogen and oxygen gas for us. And why is one tank filling with gas faster than the other? In fact, 2-to-1 ratio. Any idea? Yes.
You have 2 hydrogens for every oxygen?
Yeah, so we have twice as much hydrogen being produced compared to the oxygen. And that's stoichiometry, and that's Avogadro's law that equal number of molecules will create the same volume So since we have twice as much, so hydrogen is going down faster than the oxygen. I think it looks like faster because, and we'll just give this a minute or two. In fact, one gas has already gone down, and the other one hasn't gone all the way down. But if the first law is correct, all this energy that was stored in the sun, that was collected by the solar panel, has been created into the electrical energy. And all that electrical energy went to the fuel cell and created hydrogen and oxygen, which chemicals store the energy. And all this stored energy then can be used later as electrical energy, which then can be used as mechanical energy. So you can store energy that can be used later, like at night, so where you don't need the sun, so you can still go to the mall, still can go to the movies, or wherever you want to go at night, which is fine, because we'll leave the sun off, and it looks like we got enough to I'm going to hook up the motor. This is a front wheel drive. It's also kind of neat because you all can't see it, but it likes to run into the walls and then backs up or turn around or whatever. So we've stored the energy that was from the hydrogen and oxygen. But instead of lighting a balloon, which would release all that energy, the fuel cell is controlling the energy that's stored to the point where you don't get a big explosion. And that's one of the problems with designing automobiles is you're carrying explosive substances. That's a problem. So when you have a crash, you may have that problem. Okay? So then this stored potential energy is being converted into electrical energy, which is converted into mechanical energy. And the car goes around. And that's kind of fun. Better if you all were able to gather around and see it. Oops. So it runs into things, and so it will turn for you automatically, and then it will run into the wall. So any questions about this conversion? Now, the second law of thermodynamics will explain why we lose energy along the way. It's not really lost. First law of thermodynamics says, you run into walls, you turn around. No, it says energy converted between these different forms. So is there any questions about this?
All right, thank you. So as Dr. Lyle mentioned, there are actual losses in here that have to do with converting this ordered energy into disordered energy or heat. And we'll come back at the very end of the semester and talk about something called free energy, which is actually the energy, say, in a chemical reaction that's available to do work, like driving an engine. Okay. And he actually used to do the hydrogen balloon thing in here, but it's a little excessive. You can just take hydrogen in a balloon and light it. It blows up with the oxygen in the air, but if you fill a balloon with hydrogen and oxygen, you kind of have to close your ears, and the concussion's a little frightening, and people in the building don't know what's going on, so we can stop doing that. So, but it's very exciting. It's the big boom reaction. Okay, so we're also going to talk about energy flows and changes. So we have these different kinds of energy, but we can have energy changes or flows that we tend to divide into two different kinds of pieces. There's heat, which we're going to call Q. So I can have heat, which is thermal energy that flows, say, from a hot object to a cold object. We'll talk about the directionality of that later on. And then there's work. And work has to do with the change in the potential energy. That's related, for example, to mechanical energy. The only work we're going to consider this semester is what we call pressure volume work, which we'll talk about in a little bit. So when we're talking about thermodynamics and looking at the overall changes in a system, like a chemical system, we talk about thermodynamic processes going from one state to another. And what we mean by that is we start with some initial equilibrium state, and I'm going to use a bunch of abbreviations just because equilibrium is awfully long to write. So if you have a question while I'm writing on the board or can't read something, don't be bashful, raise your hand and say, what on earth is that? And I'll try and explain, okay? So we start with an equilibrium state, and we go through some process which proceeds along a particular path to a final equilibrium state, where I have some initial state, which I define by things for chemicals, and like the initial pressure, temperature, volume, number of moles. So I would have my system all settled down so that it had a uniform temperature, volume. I undergo some sort of a change, and during that change, things could be swirling around, and there could be a mess going on that's hard to explain. But I end up in some final equilibrium state where the system settles down again, and I have some final state that I can define in terms of a few variables like pressure, temperature, mole, volume. Okay, so that's what we mean by a thermodynamic process. So what the first law of thermodynamics says, which Dr. Lyle has sort of mentioned, is a few different things. One is that energy is conserved, neither lost nor gained. And we can describe that in terms of several different statements that are related to the first law of thermodynamics. At the end of the semester, we'll see that there are two other laws, very cleverly named the second law and the third law, and we'll talk about those. But for now, the first law of thermodynamics says a few things. First, it says there's something called the internal energy for an object that we can talk about. So the internal energy is a macroscopic energy, but it's basically the sum of all the energies, potential and kinetic, of all the molecules in the system. And so we have this thing we call the internal energy. Our text uses the old symbol for this, E. A lot of texts and modern thermodynamics uses the symbol U, but we're going to use E because that's what our book uses. And so this is basically the sum of the potential and kinetic energies of all the molecules in some sort of system, container. And it has a couple of properties. It's extensive, meaning that the value of this depends on how much stuff you have. So if I have a block of ice that's small, it has a certain internal energy. If I took a block of ice that was twice as big, it would have twice the internal energy. Okay? On the other hand, if I had two blocks of ice, they might have the same temperature, and the temperature doesn't depend on how much stuff I have. So that's called an intensive variable. The internal energy is extensive, and it's also something that's a bit subtle, but important. We won't dwell on this excessively this semester, but it's called a state function, meaning that it has a unique value for each state of the system, like pressure, temperature, volume. And this also means that if I start with an initial state and go to a final state, that the change in the internal energy just depends on where I end up and where I start, and not on the particular path I take between them. And so what it means is delta E for a process is just the final value of internal energy at equilibrium minus the initial value, and this is independent of the path I take between the initial and the final state. It has units, and most often the units we use are either joules or kilojoules. We use those quite a bit. So the first law starts by saying there is this thing called the internal energy, and we'll use it a lot this semester. Second thing it says is that the internal energy is conserved. Dr. Lal used that word. And to understand what that means, let's divide up and imagine universe, everything that's relevant to an experiment, into the part of the universe that we're interested in. We'll call that the system. And then there's the so-called surroundings, which is everything else that that system interacts with. Okay? So in order to understand this, we're going to say that we have a universe, which we might make up and define by taking the object we're interested in, putting it in a box, and separating that box from the rest of the universe. So for us, the universe would be the box and the stuff that's in it. And we're going to divide that up into the system and the surroundings. And as we'll see when we get to the first applications on Friday, we'll do a demonstration, and we'll see that you can divide that up in your head in different ways, and that has different consequences. But just schematically, what we'll do is we'll say that the universe is everything in this box. I have the system, which is the part I'm interested in, and then there's the surroundings. And this system and the surroundings can interact with each other potentially. So that whole thing is a universe. And when we talk about systems, we talk about different kinds of systems, and different kinds of systems have to do with how they interact with the surroundings. Okay? So I can have different types of systems which are related to the boundaries around those systems. So this is just sort of language at the moment. So I'm going to imagine that I have flows of some sort between the system and the surroundings that might be allowed or might not. So I can imagine that I have a flow of matter between the system and the surroundings, and I have a flow of energy between the system and the surroundings. And so if I have what's called an open system, I can have both matter and energy flow. So if I had a beaker that was open to the atmosphere in this room, energy could flow in and out of it to things, and molecules could flow in and out of it, right? I can have what's called a closed system. So if I took that beaker and I put a top on it, there could still be energy that would flow in and out of the walls of that beaker, but matter wouldn't be able to get out because I've got a top on it. So that would allow energy flow, but no matter flow. Whoops, closed. Yeah, and then I can have an isolated system. So if I took that same beaker and I put it inside of a thermos that was completely cut off in terms of energy flow from the surroundings, and I put a top on it, then I would have no matter flow and no energy flow, and the system would be completely isolated from the surroundings. Okay? So that's a little bit of lingo that we talk about. And so now that we have those quantities, we can define the first law through a couple of more mathematical statements. And I like to do this two different ways. There's what I call the global view, where we look at the whole kit and caboodle, as my mother used to say, universe with the system and the surroundings. And the statement here is that the energy of the universe is constant. And so I can write the change in the energy of the universe, which would be related to the sum of the changes in the system and the sum of the changes in the surroundings. saying is overall that energy has to be zero. So I can have energy that flows from the system to the surroundings, from the surroundings to the system, back and forth, but overall there is no change to the energy of the universe, okay? And so what that means is that whatever change in energy of the system there is, that has to be compensated for by an equal and opposite change in the energy of the surroundings. Okay, so that's one way to look at this. The other way to look at it is to take a system-oriented point of view. So you're sitting inside the system, you're the system, and there's the surroundings out of there. Your energy goes up or down because energy flows from the surroundings to you or vice versa, okay? And as I mentioned earlier, we're going to talk about two kinds of flows. There's thermal energy or heat, and there's work that's done by the system or the surroundings. And so we can take a different point of view and take a system-oriented view. And in the system-oriented view, my energy in the system might change. Why is it going to change? It's going to change because there's heat that flows from the surroundings into me, or the other way around, and there's work that's done by the surroundings on me, or the other way around. And so in the system point of view, we say that delta E for the system, we'll eventually drop this little subscript, is equal to the heat that flows and the work that's done. And in thermodynamics, the signs, S-I-G-N-S signs are really important, plus minus. And so we're going to say that Q is positive when heat flows into the system. That makes the energy of the system go up, right? So Q greater than 0 means that heat goes from the surroundings into the system. And we're going to say that W greater than 0 means the surroundings do work on the system and raise the energy of the system. So if I go back to my picture of the universe, and here's my system, and here's my surroundings, heat flowing into the system from the surroundings is greater than 0. If heat flows in the opposite direction, it makes the energy of the system go down, so that would be negative. And likewise, work is greater than 0 where the surroundings do work on the system and raise its energy, and it goes the other way around when the system does work on the surroundings. So what if I have an isolated system? In an isolated system, there's no energy that goes back and forth between the system and the surroundings. And so for an isolated system, delta E for the system is equal to 0. All right, so we got these two kinds of flows. I'm talking about heat and I'm talking about work, but we haven't really defined them yet. So let's go and talk a bit about heat and work and what they are and what they mean. And we're going to focus, as far as work goes, just on pressure volume work in this course. Although if you really want to understand things like Dr. Snell's car, as you saw, there's energy flow, so you can have electrical work, you can have electromagnetic radiation that's doing work, mechanical work, all that sort of stuff. But let's talk about heat first, Q. So what happens when heat goes into an object? If I have an object, and let's say I have a piece of ice and I drop it in my coffee, how does the ice change? What changes about the ice? Temperature goes up, right. So when you put heat into an object, the temperature goes up. If you take heat out of an object, the temperature goes down. And so we can define a relation between heat and the change in temperature of an object. And so there's a proportionality that's called big C, which is the heat capacity. So the heat capacity is something about that object that tells you how much the temperature changes when a particular amount of heat flows into it. That depends on the particular object. So a piece of ice might change its temperature when heat flows into it by a certain amount, but a chunk of iron is going to change by a different amount, okay? And so delta T here would be the final temperature in some process minus the initial temperature. This big C is called the heat capacity. It depends on the particular material that you're looking at, and it's also extensive. It depends on how much stuff you have. So if I have a chunk of ice that has a particular heat capacity, if I have a chunk that's twice as big, it will have twice the heat capacity. That can be inconvenient sometimes, and so I can also define a big C, that is the heat capacity for a particular amount of material, that's equal to the mass of that material times the heat capacity per mass. That's called the specific heat capacity. If I know that for a particular kind of material and I want to know what the heat capacity of X grams is, I just multiply that. Or I can define the molar heat capacity, which is also proportional to that. So I can kind of change from an extensive quantity to something that's nominally intensive. All right. So there's heat. We have to worry about that, and we'll talk a little bit more about heat and heat capacity in a second. We also have work, which we've talked about. And so the kind of work that we're going to think about in this class is what's called pressure volume work. And the easiest way to think about that is in terms of some material that's inside of some sort of piston or something. And so we're going to be concerned with work that occurs and pressure volume work. And we're only going to consider two different kinds of work. In general, work gets kind of complicated and you have to do line integrals and all sorts of cool calculus stuff to figure it out. But this is general chemistry, right? You haven't had that. And so we're really going to look at two different cases that are very common in chemistry. So in chemistry, I sometimes carry out a process in a closed vessel. And when I carry out that process, that means there's going to be no volume change overall, right? The volume is contained in there. Or I might carry out something in a vessel that, say, is open to the atmosphere. And so there could be a change in volume of my material. And that might be associated with doing that against an external pressure. So if I carry out a reaction in a piston, like in a car, carry out that reaction, maybe I convert liquid into gas. What's going to happen to that piston? It's working against the constant pressure, it's going to expand, right? So I have a change in the volume against a constant pressure. So those two cases we're going to look at are constant volume process. In a constant volume process, there's no change in volume, and consequently, if you go through the details of working out the work, there's no work done. There's no moving against an external force, okay? If, on the other hand, I have a constant pressure process, it turns out that the work that's done is minus the pressure times the volume change, okay? So what do we mean by this? So let's say I carry out this process where I have a liquid in some sort of container, and I carry out a process, there's pressure down on this, and my gas expands against that, and the volume gets bigger. And when the volume gets bigger, what's happening is that that system in there, as its volume gets bigger, is pushing against the external pressure. It's exerting a force. To exert that force, I have to use up some of the energy in the system. So if delta V gets bigger, P is positive, there's negative work being done on the system, meaning that the energy of the system goes down because it's doing work against the surrounding. In contrast, if I had a gas inside of a piston and I were on the outside and I pushed down on that gas, I'm the surroundings, I'm doing work on the system, what happens is I put energy into the system and the energy of the system goes up. That would be a case where delta V would be less than 0. There's a minus sign here, so work is positive. So for me anyway, keeping track of the signs on this, I tend to think of pistons and whether the system is doing work by pushing and expanding against the surroundings, or whether the surroundings are doing work by pushing against the system. Okay, so that's one way to try and keep the sign straight. Okay, so we got work. This one is sort of easy to talk about because we can see a volume change, or we know what's going on with the pressure. Calorimetry is a little bit more subtle, or excuse me, heat capacity is a little more subtle. And so how do we measure changes in Q? The way we measure changes in Q is by hooking our system up to some sort of surroundings and looking at heat flows between the system and the surroundings for a particular process. And that is called calorimetry. You'll do some calorimetry in the lab this semester, playing around with hot and cold packs, using chemistry to try and cool things down or heat things up. And so calorimetry is all about measuring heat changes, or changes in internal energy, flows between the system and the surroundings. So what I do to do calorimetry is I have my system and I have my surroundings, okay? And so I have typically a chemical reaction that I'm interested in, and I carry out that chemical reaction inside of my calorimeter. And the calorimeter, as you'll see, might be an open one to the atmosphere, it might be a cup, styrofoam cup with some water in it, carry out a chemical reaction, and then I can measure the change in the temperature of the water. Or I can do what we do in the physical chemistry lab, which is easier for things like burning gas or something. You have a closed container, like a big metal container that you can pressurize with oxygen. Maybe you want to know what the heat change for a burning of glucose is. Okay, we'll talk about that in some applications. Take a chunk of glucose, you make it into a pellet, put it inside of this big thing, put that in a bucket of water, carry out the reaction. Now the volume can't change. There's heat that's created that flows into the surroundings, and you measure the temperature change of the surroundings. The water, you know what the heat capacity of the water is, and so you can work backwards to figure out what the heat was given off by that reaction. So we're going to be really interested in the heat associated with reactions this semester. And if I have these together as a closed or isolated system from the surroundings, then any change in the heat of the chemical reaction has to be offset by a change in the calorimeter. So the energy of the reaction is minus the energy of the calorimeter. How do I calculate the energy change of the calorimeter? I come back over here. What I have to do is figure out what the heat capacity of the calorimeter is. I can do that by carrying out an experiment. And I can measure the change in temperature. So this is just minus whatever the heat capacity of the calorimeter is times the change. Okay, and you're going to use that on some of the sampling problems and other things, and also in the lab. As I mentioned, we have two different kinds of processes that we often talk about: constant volume and constant pressure. And it turns out that the way things change in terms of the energy is different whether we carry out a constant pressure process or a constant volume process. So if I have a constant volume calorimeter, that's called a bomb calorimeter. There's a little picture of one in the text. That's the idea I mentioned, where you have some closed vessel and you carry out a reaction in it. Its volume can't change. So we know that delta E is equal to Q plus W, right? So what did we say earlier? If the volume doesn't change, what's the work for that process?
Zero.
Zero, okay? So at constant volume, the constant volume heat that's given off is delta E minus W, and for constant volume, that's zero. So when I measure the heat that's given off by a chemical reaction inside of a closed container, I'm getting a direct measure of the change in the internal energy of that substance, okay? Change in all the potential kinetic energies of the molecules. That's one kind of calorimeter. There are also constant pressure calorimeters, and you're going to, I think, do this one in the lab. So an example of that would be a styrofoam cup with water in it, thermometer so you can measure the change, maybe you take some substance and you dissolve it in there, and the change in that chemical reaction results in a change in the temperature of the water, okay? But now I'm open to the atmosphere, so there could be a volume change associated with that, and so the work would not be zero. So again, if I want to do this, I can write that the change in the heat at constant pressure is equal to delta E minus W, but the work that's done now is not zero in a constant pressure process, it's minus P delta V, so this is E plus P delta V. So when I do a constant volume process, I measure the change in the internal energy directly. When I do a constant pressure process, I have this piece, but I also have this piece. So I'm measuring some other energy change, and in chemistry we call this delta H. H is not called the energy, it's called the enthalpy. And we're going to be very interested in the enthalpy this semester because we'll often be interested in the heat that's given off or taken up at constant pressure rather than constant volume, okay? And we also will be interested at times in converting between these two things. Often they're sort of about the same within 5% or so, but it depends on the chemical reaction as you'll see when we do some applications. So I can be a little bit more formal about this enthalpy thing. And we'll do that for just a second. And I can define more generally the enthalpy in terms of the internal energy. So H is also a state function, meaning that it only depends, its change depends on where you start and where you end up. That's really convenient. H is equal to E plus PV. That's the overall definition. So what does that look like? That means that, in general, if I have the change in H for some process, that's going to be equal to the change in E plus the change in the PV product. Okay? So there's a relation between delta E and delta H in some process that depends on the change in pressure times volume. If I'm at constant pressure, which is what we talked about over there, P doesn't change, and so I can take P outside of this, and at constant pressure, this is delta E plus P delta V, which is what I said it was over here. Okay? So this definition is consistent with saying that delta H is related to the change in heat under constant pressure conditions. It's a little more general. So if I measure delta H at a particular temperature and I measure delta E at a particular temperature, how do I convert between those? I'd like to know one and the other because sometimes, say I want to know what the heat given off when I burn glucose is because I'm interested in figuring out how much my temperature is going to go up when I eat a certain food, right? And I'm at constant pressure. It's easier to burn that stuff in a closed container. If I burn it in a closed container, I measure delta E, but maybe I'm really interested in terms of my physiology in delta H. How do I get between them? I can use this relation. So it turns out that the pressure volume product, if I just have solids going to solids or solids and liquids going to solids and liquids, and I carry out a chemical reaction, their volume doesn't change much. Okay? The density is sort of the same. But if I have something where I create gas, I can create a big volume change, or if I lose gas, I get a big volume change. So this piece is primarily due to change in moles of gas overall. And if I'm at constant temperature, I can use the ideal gas law to figure out what that change is. So if I have an ideal gas, or mixture of ideal gases, I know that PV is equal to nRT. And if I'm at constant temperature, then the change in PV is equal to the change in the number of moles of gas times RT. So with that, I can stick that in this equation up here, and I can figure out how to convert between delta E and delta H. Okay, so this is part of the semester that everybody tends to get all hung up on, but we'll try and get this a couple times so that you get it. So I can set up one kind of experiment and measure delta H. I can set up another kind of experiment and measure delta E. And if I want to convert one to the other, I can do it if I know the change in the moles of gas in a particular chemical reaction. So let's go over here. And so if I carry out a chemical reaction at a particular temperature, almost at a constant temperature, so let me change a little bit, then what I have is a relation between delta H for a reaction, which we're going to be interested in during the semester, and delta E for a reaction. And that's just the change in the moles of gas associated with that reaction times R, the gas constant, times the temperature at which I'm carrying out that reaction. I can measure either one of those and get the other. So for example, if you take calcium carbonate, limestone, and you put it in a container, it will spontaneously create CO2 gas. This is an interesting reaction because if you run it in the opposite direction, you can store gaseous CO2, which we might want to do if we want to reduce it in the atmosphere. But for this reaction, what would the change in the number of moles of gas be?
Positive 1.
Positive, and it would be +1, right? Delta moles of gas equals +1. So the number up here would be 1, and I could use that then to convert between these two. Okay, if there's no change in gas moles, then delta E and delta H are almost identical. Okay, there might be a super small change. Okay, so we got all this stuff, but this is a chemistry course. We've sort of been talking about physics and heat and stuff. What we're interested in primarily is changes in energy and things associated with chemical reactions, or later in the next unit we'll talk about energy within atoms and then molecules. And if we're interested in changes in energy associated with chemical reactions, we call that thermochemistry. And you'll get good at this semester, hopefully. And so in thermochemistry, what we're interested in is delta H, and we often put little subscripts on these things to identify what we're talking about. RXN for me means reaction, okay? So I'm interested in the delta H associated with the reaction, or the delta E associated with the reaction. And if I know one of these, I can use this fancy-dancy formula over here to interconvert between them. You do have to have a chemical reaction that's specified along with a particular stoichiometry that's specified in order for this to make sense. So what are these things? Well, I start in my initial state and I go to my final state. So I start with the reactants, do something to them, and I end up with products. And so these for a reaction then would be the enthalpy of my final state, which is the products, minus the enthalpy of my reactants, and likewise delta E would be E for the products minus E for the reactants, okay? And we can measure these changes using calorimetry like you'll do in the lab. We often write down, instead of a chemical reaction, what we call a thermochemical reaction, which includes the chemical reaction itself with the specified stoichiometry and the value of delta H or delta E for that reaction. So let's look at an example. Thermochemical reaction. And let's look at the example of octane combustion, which is close to something like what happens in your car. When you're running your car and you're burning up octane, okay? So the chemical formula for octane is C8H18, and if I'm at room temperature, octane is a liquid, it's like gas that you put in your car. If I have a combustion reaction, what I do is I take that hydrocarbon and I react it with oxygen. Okay, that's what a combustion reaction is. And so I react this with oxygen, and in a combustion reaction of a hydrocarbon, what I create is CO2 gas. And if I'm at room temperature, I create water, and water is a liquid at room temperature, right? If I carry this out at a high temperature, the combustion might yield gaseous water, but at room temperature, I would have these substances. That's a combustion reaction. And to get the reaction, I have to balance this properly. If I keep a 1 over here, I've got 8 carbons, and so I have to get 8 carbons over here. I start with, it looks like 18 hydrogens. I have to get enough hydrogens on that side to balance, so I need to have a 9 here. And then I can count up the number of oxygens, and I have to have 25 halves oxygen over here to balance. Okay, so you've got to remember a little bit about balancing reactions if it hasn't happened in your head for a while. It will come back. So that's my balanced chemical reaction written this way. I've written this as 25 halves. Some of you may have been told in high school that you can't have half a molecule, so you can't possibly write it that way. But I think of these as moles, and you can certainly have 25 halves moles of something. So as far as I'm concerned, this is a perfectly legitimate way of writing this. If I measure delta H for this reaction, I find out that it's 5.50 times 10 to the third kilojoules. That's a lot of energy. Okay, that's why we like to burn gasoline. It's convenient, it's a liquid, you can stick it in your car and burn it and get a lot of energy out of it. Okay? So this is the number if I did a reaction at constant volume that I would measure. And this means this is the amount of energy that's given off each time per mole of reaction. What do I mean by per mole of reaction? Sometimes you'll see this actually written as kilojoule per mole. The way this reaction is written, it means 1 mole of this reacts with 25 halves moles of this to make 8 moles of that and 9 moles of that. That's 1 mole of reaction the way this is written. Okay? Notice that the sign is negative. If I have a negative reaction, what does that mean? Is heat going into the system or heat going out of the system? Heat's flowing out of the system, right? There's a lot of heat that's generated during this. So delta H is less than 0. Heat is given off. And that's what we call an exothermic reaction. We're going to use the words exothermic and endothermic. If delta H was greater than 0, then the system would absorb heat from the surroundings, and what would happen to the temperature of the surroundings? They would go down, right? It would cool things off. That's a endothermic. And on Friday, Dr. Lyle's going to bring in some examples of those. He's got a magic trick he does with the magic chef. Look at that sort of stuff. All right. So what would happen if I wrote the stoichiometry differently? Suppose I didn't like that 25 halves. I'd get rid of it by writing 2, 25, 16, and 18. Now when I burn 1 mole of reaction, or carry out 1 mole of combustion, I got twice as much stuff reacting, right? So the heat in that case would be twice as much as this. That's what we mean by this being an extensive quantity. So you have to be careful. You have to write down the stoichiometry of your chemical reaction in order for this delta H to make sense. If I wrote this with a 2 over there, delta H would be twice as much as it is here. And so there's an important thing here that if I multiply the reaction through by some number because I want to change the stoichiometry, I have to multiply delta H by that same number. So if I multiply the stoichiometry by some number n, I have to multiply delta H, or delta n, or excuse me, by that same number, okay? Likewise, if I reverse the reaction, so if heat's given off in this direction, if I turn this reaction around, is heat going to be given off or taken up? I'm going the opposite direction. It's going to be taken up, right? So in this direction, this reaction is exothermic, heat's given off. If I could make it go this way, then heat would be taken up, and it would be endothermic. So if I reverse the reaction, I flip the sign of delta H. And one thing that you're going to be expected to do, which we'll talk about now in this class, is to take a series of reactions and delta H's and combine them together in order to calculate delta H for something else. In doing that, you're going to have to multiply those reactions through by numbers, and eventually you're going to have to flip them around. And so these 2 points here are going to be important for that. So one of the nice things about this delta H and delta E being path independent is I can imagine taking any path I want between 2 points, and that allows me to figure out a delta H for one reaction from delta H's for other reactions. So sometimes it's really easy to measure delta H's for things like this combustion reaction, but it might be harder to measure delta H for a direct reaction between two other things. And so I can use what's called Hess's law. I'm not actually even sure who Hess is, but Hess is now famous because of Hess's law. Probably some European guy, I don't know. Anyway, it's a long time ago, right? So what Hess said is that delta H is path independent, and so I can take any path between an initial state and a final state. And that means I can get delta H for a reaction through the sum of delta H's for other reactions. So schematically, so by the way, when I said European guy, that's just a historical artifact. There's a bunch of you who can be the future Hesses of the world, and you're not just European guys, okay? You're all sorts of other people, so do it. Make history different. So if I do, somebody in here is going to win a Nobel Prize, I know. Someday. It's not going to be me. All right, so AA plus BB goes to CC plus DD. That's our generic reaction. I'll write it down way too many times on the board. I need to get a stamp some year where I can just go stamp that baby up there and not have to write it. But there's the reaction, okay? So suppose I want to get delta H for a particular reaction like this. So maybe I can't do that very easily directly, but I might be able to convert A and B into some other quantities, and that would be easy to measure, and then I could maybe convert C and D into those same quantities. So if I know how to get to some other chemicals, NN plus MM, that I could then convert to make this. The first law of thermodynamics says it doesn't matter which path I take. I can go this way, I can go this way. And so if I know delta H1 for that process, making these products, and if I take these as reactants and make those, and I have a delta H2 for this, then what the first law says is delta H for that overall process is equal to just delta H1 plus delta H2. This is a thermodynamic cycle, and we'll look at examples of these when we do some applications. And so I can use all sorts of ways, devious ways of doing this. So let's suppose I want to go from here to here, and it's easy to burn these things into CO2 and water, okay? Maybe it's easy to burn these things to make CO2 and water. If I do those two experiments, I can figure out what delta H H1 is and delta H2 is, and I can use those to calculate delta H for this process, which might be hard to carry out directly, okay? So you can use things, and a lot of them are tabulated. If you look in the back of the text, there's all sorts of appendices, lots of delta H's in them, and other things that we're gonna learn. You can use those to calculate these. People slaved away at the National Institutes of Standards and Technology for years until they were on furlough, which I guess they are now, coming up with these numbers, okay? So one useful number, one way of using that, is to use what are called delta H's of formation. And so, as an example of that, we're going to write down this kind of reaction. This is you can do things that are a little bit more general than this, and then we'll pretty much be done for today. So these have a special little symbol, and all these symbols have meanings, and there's lots of subscripts and superscripts. So we have what's called delta HF of 0. Formation. That tells me that I'm talking about a particular type of reaction, where I take elements in their standard states and react those to make some compound that I'm interested in. The little 0 means standard state. We're not going to worry about that a lot this semester, but a standard state means that a gas is at 1 atmosphere at some particular temperature. I have a pure liquid, pure solid. So for example, suppose I'm interested in the delta H of formation for octane. Okay? What is the delta H of formation of octane? It's the delta H when I start with elements in their standard forms. So what's the standard form of carbon? Is it liquid, gas, solid? It's graphite, okay? Graphite like in your pencil. Diamond is also a form of carbon, but it's actually not the stable form, but going from diamond to carbon is really, really slow, so diamonds are still a real best friend, as they used to say. There was a jeweler, I think, had that thing. So if I start with graphitic carbon, and I react that carbon to make octane, I react that with hydrogen to make octane. Delta H of formation is the energy associated with creating 1 mole of this substance. So if I make 1 mole of this substance, I have 8 carbons there, so I need 8 of these. I have 18 hydrogens, and so I need 9 of these, okay? So this would be the reaction that forms octane from its elements in their standard forms. At room temperature, hydrogen is a gas. And so delta H for this is whatever this number is when I carry out that reaction. Similarly, if I wanted to make water, like Dr. Lyle did with his car, I would start with hydrogen gas and react that with 1/2 mole of oxygen gas. And this would be delta H of formation for liquid water. If I made gaseous water, the delta H of formation would be different. Okay, so why do I care about these delta H's of formation? What's nice about them is I can do this Hess's law thing. I can start with the chemicals I'm interested in. I can turn them into their elements in their standard forms, and then I can recombine those elements to make products. So this step involves a bunch of delta H's of formation. This step involves a bunch of delta H's of formation. So if I look up those delta H's of formation, I can calculate delta H for any reaction I'm interested in. And so we can combine these things together and come up with a thermodynamic cycle that takes my reactants, turns them into elements in their standard forms, turns those into products. And by doing that and being careful about the signs of those processes, I can apply Hess's law to a reaction. And so delta H for a reaction at its constant pressure I can imagine taking elements in their standard form and turning them into the products. That would be the delta H for each of these reactions, where I make C of this product and D of that product. So that's going to be positive, so I get C times delta H of formation of the product C, plus D times delta H of formation of my product D. And then in this first step, I'm taking compounds and turning them into their elements in their standard form. That's the reverse of delta H. And so I have to subtract A times delta H F0 of A minus B delta H F0 of B. And the book likes to write this in a fancier notation. It's the sum, that's the sum symbol, of N, whatever the moles are, delta H F0 of the products, that's this piece, minus the sum of M delta H F0 for reactants, that's this piece, okay? So I can do this using delta H's for formation, that's handy. There are other types of reactions that I can use for this sort of thing. You have to be careful of the signs. We'll look at some combustion reactions on Friday and the next time. There's a delta H for that. There are also changes in delta H when I change the state of a substance, when I go from a solid to a liquid to a gas. And so there's a delta H of fusion. Fusion means melting. So if I have ice and I turn it into water, I have to put heat into that, right, to change that. And there's a delta H of vaporization, delta H of vaporization, and that would be for boiling. These two things are referred to as the latent heat of a substance, and they're going to depend on that substance. And so we'll play with those a little bit too as we go through, okay? All right, so that's the overview. You've got the text, which has a lot more detail and words and examples. I recommend if you're doing the text that you actually look at the examples as you go through when you're doing it, maybe try them. That's going to help you get that little bit in mind before you move on to the next thing. There's a bunch of problems listed at the back of the text that you can use for practice, and then you have this 14 sampling problems to work through, which will help you get that stuff in mind. Remember, on Wednesday, we're going to do the IRAT-TRAT thing, and so make sure you get the sampling stuff done in time. Come to that and be able to take this little quizzing as individuals and as samplings do tomorrow night.